Semantic Segmentation for Root Understanding by Rishabh Goyal for pattern recognition. Your problem is a task of classifying each pixel in the scene into different classes with a clear distinct boundaries between each classes. We discussed segment architecture approaches to solve semantic segmentation for road scenes. Dataset used is a Cambridge urban road dataset of 233 labeled test images for 11 classes. We aim to evaluate the merits and demerits of different architecture approaches. The architecture are relied on the memory requirements, inference times, statistical metrics, visual quality of segmentation, and classification. We also compared with the claims in the paper among Net Basic and Shadow Network has 4 encoders and 4 decoders, and the deeper has 13 layers which correspond to V16 without 3 fully connected layers, which reduce the memory bottleneck a lot. Each convolution layer is followed by a patch normalization and yellow layer here. They reduce the memory bottleneck further by introducing 2 max pooling layer with transferable pool indices, which saves memory from 134 MB to 40.7 MB and preserves translation invariance. They try different decoder variants for the architecture evaluation. The second basic discuss about use transferable max pools past map at the decoder, while another architecture decoder tried fully convolution based decoder uses encoder feature maps which could be added dimension reduced or fully stored along with deconvolution at the decoder side. The other variant segment is a fixed 64 feature map architecture in each layer which prevents any parameter explosion happening in a layer. It is also to be noted that the last layer of a decoder is a multi-channel decoder with connected encoder and decoder maps and can generate RGB or RGBT features. The input uh, is normalized locally for contrast for better convergence. The other variant is actually Bayesian segment, which adds top-out layer in a segment and segment basic encoder or decoder with perceptibility testing for weights by sample weight testing to inference. This addition is called actually Monte Carlo dropout. There are many datasets for semantic segmentation. Pascal VC12 dataset, Statistical dataset, and Sun RGB dataset are one of the few. Camwith dataset is the dataset we are using here. Recent version has 32 classes with 701 labeled images. The Camwith dataset version we use has 11 classes, which has 367 train images, 101 validation images, and 233 test images of 360 483 RGB resolution. Since the normal datasets are manually iterated, even software are used for annotation of the dataset, there are chances that there may be some discrepancy in the bugs. The 14 class label is found to be present in a place in the Camwith dataset, but there are only 11 classes. Biscale value is 11 instead of 12. Class value of tree is 4 instead of 6. Color palette below has 12 labels, remember that. And zone marking was not included for the evaluation of the dataset data provided, pre-trained dataset data provided. It is only used for the web demo, which has a zone marking label available and is trained on a much larger Cambridge dataset and much finely annotated dataset. The segment architecture will be implemented on customized cafe version with tutorial to train and test segment models. For each model, the total inference time ranged from 7 minutes to half an hour on Ubuntu 14.04. Repeated model used for evaluation. The model definition.products are segment basic Camwith 4 and 4 decoder, 64 feature maps, no load decoder. Bayesian segment basic Camwith, same as segment basic Camwith with 2 dropout at deepest and declare with sample weight testing with batch size 4. Bayesian segment Camwith is a variant of the second earlier Camwith with a simple dropout instead of a Monte Carlo dropout with the batch size reduced to 1. The third, fourth, and fifth protects are actually the variants of second and third only with a deeper network. The sixth one is the SegNet model driving web demo, which is a 13-layer version of SegNet basic Canvas trained for a larger dataset for 12 classes instead of 11, with using Xavier with fillers, which has a variance of 1 by n into input, where n is the number of input inside the layer, instead of Gaussian or MSRA segment based architecture and output probability of all 11 probability classes, while the segment basic and web demo outputs the maximum, the probability of the class which has the index of the class which has the maximum probability. The statistical parameters are global accuracy, class average accuracy, and mean detection over union. Every uncertainty image generated using sample weight test evaluation gives a higher uncertainty value for moving object than static ones in a Bayesian segment model. The variance of the Bayesian segment model with sample-based regression is as follows. All dropout layers with encoder, all encoder and decoder with dropout layers are too strong a regularizer, results in training loss. Central to encoder and decoder dropout performs best in terms of class average accuracy and interest of union. Dropout just before the softmax layer helps with global accuracy. The segment So the artificial implementation analysis is as follows. The table shows that FCN basic decoder performs 2x better than the segment basic decoder, but has a 11x higher memory requirement. This is because of the storage or encoder feature maps. FCN basic can actually be considered to be real time at 30 FPS. It can be concluded from the table that larger decoder performs better in terms of quality. Preserving encoder feature reduces reference time but increases memory requirement, as discussed in the above example. If a memory is constrained to get a better inference time, pass the damage reduce feature encoder feature map, and that could help you. The evaluation should consist of a script file that runs all the webcam demo and test patient segment pi. It also considers a tutorial master repository, which contains a logs inference logs generated for uh, all the model definitions. The can be dataset with test, train, validation, and train all the folders. Models which are pre-trained and available from the Signet tutorial are extension with cafe model.exe. These are trained weights and it needs to be tested along with the proto.txt script. The scripts folder contains the color palette images for CAM with 11 class and CAM with 12 class along with Sun RGB dataset. The other scripts present are compute.sql.m to generate statistic results, webcam.py that supports running webcam demo segment basic allows to save or display results using -save parameter. The results generated includes input image, ground truth color image, segmented class label image, segmented colored image, and horizontal feature input image and segmented colored image. The script only supports running basic segment based model evaluation due to pre-processing of the input image and allows to save or show results using -save option. The one additional image that is dumped is actually the aware acidity image. This is generated. The plot confusion matrix.py also added to generate confusion matrix whenever required visually. The inference speed and quality of the decoder lies here. Before that, we actually demo the code, the version of our demo here, which is recorded in a YouTube platform and will be played back here. We ran the script of we ran the script of the CSG here, and we found the webcam py is present here, and with model home being Background also runs segment basic cam with txt. Test Bayesian runs Bayesian segment cam with txt, while Test Bayesian also runs all other Bayesian architectures cam with W and basic cam with W. It is to be noted that we have already given a test script run of the first webcam decoder, and it takes at least 25 to 30 minutes to run this decoder in this case. The weights are given in the inference fold path by a cafe model. The color is pointed out by the CAMVIC 12 set, and input is uh, given by test.txt. So the model is saved in a inference profile is in a segment web mobile driving web terminal log. For the segment basic, the CAMVIC palette is different because there are 11 classes only. The webcam demo here has a simple folder that creates all the images folder that is required to be dumped, and then uh, it reads the input, pre-processes it, sends it to cafe architecture, and then post-processes the output to generate uh, required images. It also includes the concatenated images which are horizontally fused together, and also the predicted labels. The test Bayesian segment.py is similar to that, but it has a slightly uh, different pre-processing compared to the webcam.py. It also that's why has a higher pre-process time. Moreover, it's to measure it's generate another uncertainty image metric, which is generates max accuracy as average uncertainty as a image output. It also considers a horizontally fused output image, which could be used to evaluate the architecture side by side. These are the outputs of the segment driver which are already being generated. And one of the output we opened, we found out that the segmentation is so smooth and proper. There are one of few initial segmentation, and if we compare to input image, we clearly witness the the consistency of the segmentation in both the input and output. Now we've moved back to our PPT, which shows the results of the inference speed and quality. The pre-trained cafe models shared are not well trained except the web demo, for which the ground truth files are not there. The author tardiness in providing well-trained models with respective evaluation information questions segment stability and effectiveness for the problem. They claim to achieve a global accuracy of 80% above and the class average accuracy of 60% above and interest of union of around 45% for trained segment basic. Segment basic is fastest, but it does not matter. It doesn't matter because the quality is bad. It's below 10%. The basic segment models have a better quality for each having global accuracy of 50%, class average accuracy of 27%, and test of union of 17%. It is to be noted the average uncertainty computation for Monte Carlo point Bayesian slows down inference almost 3x but only increases the quality by 2 or 3%. The second web demo seems it's not necessarily as fast as Bayesian segment cam with W, which is a slightly shallow network but perform much better image quality at its deeper as well as more exponentially trained. These are comparisons that are shown between us. You can clearly say how much the web demo is better than the Cambridge comparison. This is a shallow network. And the segment basic Cambridge is completely destroyed. This is a ground truth version and this is the input image. It segment matches very closely to the ground truth and does not have false positive or Bayesian segment cam as Bayesian segment cam will do. It shapes the object like in different dynamic scene compared to other, but it already has lots of objects in the scene. The Bayesian segment this then the segment basic model because of the addition of two robot layer in the deepest encoder and decoder. They have conveyed various basic segment model that are trained. The segment version preserves uh, 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 Segment preserves complex boundary better than segment basic version because it's deeper. The Monte Carlo dropout architecture performs better boundary restriction and segmentation with complex shapes in the scene compared to respect architecture with simple dropout. Monte Carlo dropout loss lot on inference time compared to in simple dropout. For real-time implementation, simple dropout looks a better choice. Dropout helps regularize architecture, thus give better results. Here we present the uncertainty images of the network. A deeper network has a clearly lesser uncertainty than shallow. Deeper network have more distinct boundary than a shallow network. Uncertainty of class with moving vanishing object like a tree is more than the static or larger domain like sky or building. Inside, segment end-to-end trainable with a single part stacked encoder-based architecture is simple for semantic segmentation. Multi-part end-to-end trainable approach may capture more complex information from inputs. It suggests interesting approaches for memory comment reduction and inference time reduction. Losing 3 feet FCC layer of VG16 transferred max pool indices, not preserving encoded feature map or dimension to reduce them, fixed 64 feature map in each layer. These are the interesting approaches. Simple dropout layer increases generalization and increases quality without incurring much inference time. Ill-trained old weights in public domain limits the evaluation and reach out. New architecture comparing its line with segment has to also train segment from scratch as no pre-trained models are available for comparison. Training Segnet from scratch to compare is a risky and time-consuming job. Segnet performs well for almost fixed objects and scenes with less clutter, but dynamic objects and clutter scenes it falls apart. Can be limited and uh, small data set for training and evaluating it for complex problems, semantic segmentation for root system understanding. Redscape is a much better and much diverse dataset compared to Campbell. We plan to explore Indian bottleneck here and Tametal fire module and parallel recognition, which are multi-channel and two-and trainable layers. The table 8 clearly shows which taken from Indian evaluation that Indian performs better for Campbell dataset compared to segment basic and segment models, though and even it has a better inference time. Cityscape data is becoming primary threat for evaluation of the artificial approach as it's used in Inet also. Semantic segmentation for road scene is a dynamic and complex problem, so architecture should be learning on the fly. We have to explore generative adversarial networks which are such models which can be beneficial for semantic segmentation. It has a discriminator module and a generator module. Discriminator distinguishes the ground truth map from generator maps. A generator function learns to generate more false flags to confuse the discriminator. Opposite to solve semantic segmentation for road scenes are evolving fast. We could see autonomous vehicles being tested in California currently. Suggestion. Suggest semantic segmentation include interesting approaches of memory requirements reduction and inference time reduction. Losing 3 accuracy layers of G16, transfer max pool index is not preserving encoder feature map and dimension reduce them 664 feature map in each layer. Suggest designed to focus on real-time performance and memory concern rather than just quality. It fails to achieve real-time performance on high-end GPU like that but so embedded GPU is still far away. Bayesian FFV.sample test gives a balance between quality and inference time. Poor maintenance of well-trained weight model is messy and risky for evaluation and comparison with new approaches. Semantic segmentation for road scene is more a dynamic problem with scene with lot of clutter. Extensive label and device dataset like Cityscape dataset are required to train and test along with the interesting approaches. This presentation. Thank you.